Hi everyone! In this video we're going to start learning about exponential functions and their graphs. An exponential function has the following form. f of x equals a to the power x. In other words, it's a real number that's being raised to the power that contains a variable. Or I can say an exponent that contains variable. Well, that's where the name of the function comes from. And there are certain restrictions to what this number, we call it the base, can be. This number should be always greater than 0, a is greater than 0, and it cannot be equal to 1. Think what happens if we start raising 1 to different powers. Well, it's just going to be a constant function, 1. Here are two examples of exponential functions, f of x equals 2 to the power x, and g of x equals 1/2 to the power x. Let's look at how graphs of these two functions look like. Let's find and plot points for the graph of the function f of x equals 2 to the power x. These are the x values that I'm going to use. When x equals -3, to find the corresponding y value, I have to take 2 and raise it to the power -3. That's because I take 3 and plug that into the function for x. Every time when I raise the number to the negative power, I first have to rewrite it with a positive power. That I'm going to write 1 over 2 to the power 3, and that's the same as 1 over 8. So the first point that I found for the graph has the x-coordinate -3 and the y-coordinate 1 over 8. And in the same manner, I found the corresponding y-coordinates for the x values -2 and -1. When x equals 0, to find the corresponding y value, I have to raise 2 to the power 0, and that equals 1. Any number raised to the power 0 is always 1. When x equals 1, 2, and 3, I got the corresponding y values 2, 4, and 8. Let's plot all these points. Here they are, and I can see the pattern, so I should be able to connect those points. The only part of the graph that I have to think about is right here. When I extend the graph to the left, is it going to cross the x-axis and going to go down or not? Let's think about it. If I pick smaller and smaller x values like -4, -5, -6, and plug them into the function, what kind of y values I'll get? Well, all those negative x values become powers of 2, and we just talked about how when we applying a negative power, we'll have to rewrite the expression as 1 over 2, and then the power becomes positive in the denominator. So I can see that as I plug in all those negative values for x, -4, -5, and so on, I will always get a fraction, 1 over, and the denominator will keep growing. So while the overall quantity becomes smaller and smaller as the denominator gets bigger and bigger, the number itself stays positive. So this tells me that the left end of this exponential function will be getting closer and closer to the x-axis, but it will not cross it. It will stay above it, like this. And that's not all. The fact that the left end of the graph approaches the x-axis while never crossing or touching it makes the x-axis the horizontal asymptote for this graph. Okay, now as we see the graph, it will help us to describe the domain and range of the given function. Since this graph extends to the left and to the right without bound, this means that the domain includes all real numbers. How about the range? Well, while the graph goes up without bound, it is bounded by the x-axis down here. So what can we say about the possible y values of this graph? They will be in the interval from 0 to infinity, and that's the range of the given function. Next, let's look at the graph of the function g of x equals 1 over 2 to the power x. Again, we're going to find and plot several points that belong to the graph. When x equals 3, to find the corresponding y value, I have to raise 1/2 to the power -3. For that, I'm going to take the reciprocal of the fraction, or flip it. In other words, it's the same as 2 over 1 to the power +3. The denominator 1 I can drop, so that's 2 to the 3rd power, or 8. Same way I found the corresponding y values for x equals -2 and x equals -1. They're 4 and 2 respectively. When x equals 0, I need to raise 1/2 to the power 0, and that's always 1. And for the other three x values, the corresponding y values are 1/2, 1/4, and 1/8. Let's plot all these points. I can notice a similar pattern as in the first graph. However, this time the line is getting closer to the x-axis as the x values are increasing. And I have the same question. Will the graph cross the x-axis? What happens when I plug in x equals 4, 5, 10, 100? So as the power 1/2 gets larger and larger, this will make the denominator grow. And that means that the resulting functions will be getting smaller and smaller. No matter what power of x I use, I will never get 0 as the result. That means that the graph will neither touch or cross the x-axis. Here's the graph itself. And because of its behavior around the x-axis, it makes it the horizontal asymptote of this graph as x approaches positive infinity. In other words, as x values are increasing without bound. What's going to be the domain and range of this function? In regard to the domain, we see that the x values are increasing without the bound and decreasing or extending to the left without bound. Therefore, the domain includes all real numbers. And same as in the first graph, the y values will stay neutral from 0 to infinity. That's going to be the range of the given function. Let's think about what other interesting facts we can observe about these graphs. First of all, we can see how the first graph is increasing and the second graph is decreasing. And that's something that can be generalized. The graph of any exponential function is increasing when the base is greater than 1, when this number is greater than 1. And the exponential function will always be decreasing when the base, or this number, is between 0 and 1. The reason I didn't say just simply less than 1 is because we know that the base, or a, has to be positive. And there is one more interesting observation. Notice how both graphs cross the y-axis at 1. In other words, it's the y-intercept of both graphs, 0.01. Do you think it's a coincidence? Well, of course it's not. Both points were obtained when we let x be equal 0. And for the exponential function, that means that the base, for the first one it's base 2, for the second function it's the base 1/2, are both raised to the power 0. And we talked about how any number raised to the power 0 equals 1. So no matter what base the exponential function has, when x equals 0, the corresponding y value will always be 1. So we can conclude that all graphs of the exponential function y equals a to the power x would go through the point 0, 1. In other words, cross the y-axis at 1. There are a few more things that we can mention about the graph of an exponential function. On these two pictures, we can see graphs of exponential functions with bases that are greater than 1 and bases that are less than 1, or I should say between 0 and 1. We already talked about how for the first group of functions, the graphs will be increasing, and for the second group, the graphs will be decreasing. As you can see, they all go through the point 0, 1. All of those numbers raised to power 0 equal 1. For all these graphs, the x-axis is the horizontal asymptote, which means that the range will be from 0 to infinity for all of them. But what's different about those graphs is their steepness. Notice that when we have bases that are greater than 1, greater the base, closer the graph to the y-axis, so it's steeper. When bases are between 0 and 1, smaller the base, or closer to 0 it is, steeper the graph. And let's briefly talk about some other variations that we can observe in an exponential function. Notice how for all those three functions, it's not just base raised to the power x. For the first one, we have 3 added to the basic function 2 to the power x. In the second one, we have 3 added right next to x within the exponent. And for the third one, we have a negative sign placed in the front. You might already know that all these adjustments will make the graph of the basic function 2 to the power x to transform in a certain way. Let's look at this. When we have a number added to the basic function, it makes its graph move up. So what we have in green is the graph of the function y equals 2 to the power x plus 3. We can obtain it by taking points of the basic graph and shifting them 3 units up. Well, because of that, the original asymptote, that's the x-axis, is also being shifted 3 units up. So the graph of this function has the horizontal asymptote y equals 3. And that means that the range of this function will be different. While the domain is still the same, all real numbers, The range is from 3 to infinity, not including 3, because this graph will never cross or touch the line y equals 3. And you might guess that if the number was subtracted from the basic function, then the graph would be shifted down that many units. The graph of the next function can also be obtained from the graph of the function y equals 2 to the power x, but this time it will be shifted horizontally. And specifically, the graph of the basic function y equals 2 to the power x will be shifted 3 units to the left. This is called horizontal translation. When it occurs, we always shift in the opposite direction of the number that's being added or subtracted right next to x. Plus 3 means to the left, minus 3 would mean shifting to the right. And because we only shifted the graph horizontally, the domain and range of this function are the same as the domain and range of the basic function. And finally, the function where we have a negative sign placed in the front. This negative sign indicates the reflection. To obtain the graph of this function, we simply take the basic graph and reflect it over the x-axis. The domain of this function is the same as for the basic one, from negative infinity to positive infinity. All real numbers. But what can we say about the range, or all possible y values, for this function? Well, since the graph is positioned below the x-axis, and it will never gonna cross or touch it, the range of this function is the interval from negative infinity to 0. Keep in mind that we always read the vertical axis from the bottom going up. That's why it's from negative infinity to 0. Okay, so these are some additional examples of exponential functions and their graphs.